October 2025, multiple observatories worldwide. An interstellar visitor, 3I, Atlas, is passing through our inner solar system, offering scientists a rare opportunity to study material formed around another star. After its closest approach to Mars, many expected immediate public announcements. Instead, there's been a coordinated pause, not because of secrecy, because raw telescope data requires weeks of calibration, cross-checking, and verification before anyone can draw reliable conclusions. This is how science actually works when the observation window is difficult and the stakes are high. No shortcuts, no drama. Just the careful process of separating signal from noise when a once-in-years target passes through one of the hardest viewing geometries possible near the sunday. Let's start with what's confirmed. 3I, Atlas is real. Its trajectory is well established. Multiple independent observatories have tracked its path, and the orbital elements all agree. This object originated from outside our solar system. Its hyperbolic orbit, meaning it's moving faster than solar escape velocity, proves it's just passing through. It arrived from interstellar space, and it will return to interstellar space. We know its approximate size. Current estimates place the nucleus somewhere between 1 and 3 kilometers across, though precise measurements are difficult when the object is partially obscured by its own outgassing. We know it's active. 3I. Atlas is releasing material, primarily water vapor, along with dust, creating a visible coma that extends thousands of kilometers from the nucleus, and we know the observation window has been extraordinarily challenging. As 3I, Atlas approached the Sun, it entered a region where solar glare makes direct Earth-based observation nearly impossible. Telescopes on our planet simply can't point that close to the Sun without risking damage or losing the object in overwhelming scattered light. This is where Mars orbital missions became critical. Spacecraft orbiting Mars, positioned differently relative to the Sun, had brief windows where they could observe 3I Atlas from angles Earth-based telescopes couldn't match. Those observations happened. The data was collected. But raw data isn't science yet. So why the communication gap? Why aren't space agencies releasing everything immediately? Because turning photons into knowledge requires something most people underestimate: time. Here's what happens after a telescope captures an image or spectrum. First, calibration. Every detector has imperfections, hot pixels, sensitivity variations, background noise. These must be mathematically removed using reference observations taken under controlled conditions. Second, atmospheric correction. For ground-based telescopes, Earth's atmosphere distorts incoming light. Water vapor, turbulence, thermal gradients, all of these must be modeled and subtracted. Third, co-registration. When multiple telescopes observe the same object, their data must be aligned to a common reference frame. This requires precise knowledge of each instrument's pointing, timing, and optical characteristics. Fourth, spectral extraction. If you're measuring the composition of 3I, Atlas's coma, you need to separate the comet spectrum from background starlight, zodiacal light, and instrumental artifacts. Fifth, independent verification. Before publishing results, teams send their data to collaborators at other institutions who reanalyze it using different software pipelines. If the conclusions match, confidence increases. If they don't, someone made an error and it must be found. This process takes weeks, sometimes months. It's not bureaucracy, it's rigor. Because publishing incorrect data creates confusion that takes years to untangle. One rushed press release claiming an unusual chemical signature, later revealed to be a calibration error, can spawn countless follow-up papers, media stories, and public misconceptions. Space agencies have learned this lesson the hard way. So they wait. They check. They verify. And only then do they speak. But while we wait for the Mars-based data to be processed, Earth-based telescopes have continued tracking what they can measure. and some of those observations are raising intriguing questions. Let's be precise about the difference between confirmed data and preliminary hypotheses. Confirmed. 3I. Atlas is releasing water vapor earlier in its trajectory than typical comets from our solar system. Multiple independent spectra show H2O emission lines at distances where most solar system comets would still be inert. Hypothesis requiring verification. The early outgassing may indicate an internal structure with higher thermal conductivity than we typically see, perhaps more porous ice, or a different ratio of crystalline to amorphous water ice. This is plausible. Comets formed in colder interstellar environments might retain structural properties that allow heat to penetrate more efficiently. But until we have detailed thermal models fitted to multi-wavelength observations across different solar distances, it remains educated speculation. Confirmed. Some observers have reported secondary objects appearing to move near 3I, Atlas's primary nucleus. Hypothesis requiring verification. These could be fragments from a recent breakup event, possibly triggered by thermal stress or rotational instability as the comet approached perihelion. But the data quality has been limited by the solar glare problem. We need clearer images, preferably from multiple angles and dates, to determine whether these are genuine fragments, optical artifacts, or background stars misidentified due to the challenging viewing geometry. Confirmed. Spectroscopic observations show a faint greenish emission in the coma. Hypothesis requiring verification. Preliminary analysis suggests this may not be the standard C2 emission we see in most comets. If confirmed, it could indicate a different carbon chemistry, perhaps reflecting the unique composition of the molecular cloud where 3I, Atlas's parent star system, formed. But spectral analysis near solar glare is notoriously difficult. Scattered sunlight can mimic or mask emission lines. Independent verification from instruments with different response characteristics is essential before drawing conclusions. If you want to follow the real story of 3I, Atlas, not speculation, but actual confirmed data as it's released, subscribe now. I'll be covering every major update with clear labels separating fact from hypothesis. Hit like if you appreciate science done carefully. Let's talk about why Mars orbital missions were so important during this observation window. As 3I, Atlas approached the Sun, Earth-based telescopes faced an impossible geometry. Observing anything within roughly 30 degrees of the Sun is extremely difficult. Within 15 degrees, it becomes nearly impossible without specialized space-based instruments. But Mars, positioned differently in its orbit, offered a brief advantage. Spacecraft like the Mars Reconnaissance Orbiter, MAVEN, and potentially instruments on the HOPE orbiter had viewing angles that Earth couldn't match. These missions aren't designed for comet observation. They're planetary science missions focused on Mars itself. But their cameras and spectrometers can be repurposed for targets of opportunity when the geometry allows. The challenge is coordination. Each spacecraft has a primary mission. Telescope time is allocated months in advance. Pointing a camera at a passing comet means delaying or rescheduling planned Mars observations. This requires approval from multiple teams, often across different space agencies and funding organizations. When approval happens, observations are scheduled. Data is collected. And then the real work begins. Extracting useful science from instruments that weren't optimized for this task, calibrating them against reference stars or known spectral standards, and determining what conclusions the data quality actually supports. This takes time, but the potential payoff is enormous. Observations of an interstellar comet during a geometry window that won't repeat in our lifetime. So when will we see results? And what should we expect when the data is finally published? The answer depends on what teams prioritize and what the data quality allows them to confirm. 3I, Atlas will emerge from solar glare in December 2025. By then, it will be moving away from the Sun, cooling down, but still active enough for detailed study. Here's what scientists will prioritize. high-resolution spectroscopy. Teams will target specific emission lines to determine the precise composition of the coma. Key molecules include water, carbon monoxide, methane, ammonia, and various carbon-bearing species like CN and C2. By comparing these ratios to solar system comets, we can infer how the chemistry of 3I, Atlas's birth environment, differed from ours. Polarimetry, measuring how light scatters off dust particles in the coma, reveals information about grain size, shape, and composition. This tells us whether the dust is similar to solar system comet dust or fundamentally different. Rotational light curves. By tracking how 3I, Atlas's brightness varies over time, we can determine its rotation period and potentially detect irregularities in shape or outgassing patterns. Fragment tracking. If secondary objects are confirmed, precise astrometry will reveal whether they're gravitationally bound to the nucleus or drifting away. This constrains models of how the breakup occurred and what holds or held the system together. Thermal modeling. Combining observations across infrared, visible, and ultraviolet wavelengths allows scientists to model the comet's internal temperature distribution and outgassing behavior. This tests hypotheses about its internal structure. None of these measurements will happen overnight. Each requires careful observation planning, optimal weather conditions, and weeks of data reduction. But by early 2026, we should have a much clearer picture of what 3I Atlas actually is and what it tells us about the diversity of comets across the galaxy. But perhaps the most important lesson isn't about 3I Atlas itself. It's about how science responds when extraordinary claims require extraordinary patience. Some will interpret the current communication gap as evidence of a coordinated information blackout. They're wrong. Here's what's actually happening. Multiple teams collected data during the Mars observation window. Those teams are now independently analyzing their results. Before releasing findings, they're comparing conclusions with collaborators to ensure consistency. This is called peer review, even before formal publication. When results finally appear, they'll likely emerge as papers submitted to journals like the Astrophysical Journal or Nature Astronomy. These papers will undergo additional peer review by external experts who assess whether the data supports the conclusions. Only after passing this multi-stage verification process will results be officially published. In parallel, space agencies may issue press releases summarizing the findings in accessible language. But the primary scientific communication happens through journals, conferences, and preprint servers, not press conferences. This system exists for a reason. It filters out errors, curbs premature speculation, and ensures that what enters the scientific record has been thoroughly vetted. It's slow, sometimes frustratingly so, but it works. The current pause isn't agencies hiding information. It's scientists doing their jobs correctly. So here's the honest summary of where we stand today. Confirmed fact, 3I, Atlas is an interstellar comet on a hyperbolic trajectory. It will not return. Confirmed fact, it is outgassing water vapor and dust, creating a visible coma. Confirmed fact, Earth-based observation during solar approach was extremely limited. Confirmed fact, Mars orbiting missions had better viewing geometry during critical windows. Plausible but unverified. Early outgassing suggests unusual internal structure. Plausible but unverified. Secondary objects may represent recent fragmentation. Plausible but unverified. The greenish emission may indicate non-standard carbon chemistry. Requiring more data. Precise composition ratios, dust properties, rotation state, fragment dynamics. That's the current state of knowledge. Not exciting, not dramatic, but honest. And honesty is what science owes the public, especially when dealing with rare events that spark intense curiosity and speculation. The real story of 3I Atlas isn't about what we know today. It's about what we'll learn over the next 6 months as more data arrives, more teams publish results, and our picture of this interstellar visitor gradually sharpens. 3I. Atlas will fade as it moves away from the Sunday. Eventually, it will become too faint for even our largest telescopes. But the data we collect now, carefully, methodically, rigorously, will remain. It will inform our models of cometary composition. It will constrain theories of how other star systems form and evolve. And it will remind us that the universe still holds surprises, but understanding them requires patience. No shortcuts, no drama. Just science done right. Which aspect are you most curious about? The thermal models, the dust analysis, or the potential fragment dynamics? Let me know in the comments. And if you want coverage of the December observations when 3I Atlas emerges from solar glare, subscribe now because that's when the real data collection begins.